In this lesson, you are going to solve this question I have on the screen. The question says that a rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kJ. During the cooling process, the fluid loses 500 kJ of heat and the paddle wheel does 100 kJ of work on the fluid. Determine the final energy of the fluid. Neglect the energy stored in the paddle wheel. So we've been told to neglect the energy stored in the paddle wheel. So I'm not going to consider that energy in this case. So now let's focus on the actual question. So you have a rigid tank which contains a hot fluid, okay, and then this hot fluid here is being stirred. Okay, it is being stirred, and then being told that initially the internal energy of the fluid was 800 kilojoule, and then during the cooling process, the fluid lost 500 kilojoules of heat because of the stirring, and then the paddle does a work of what 100 kilojoule on the fluid. We should determine the final internal energy of the fluid. So let's look at what you are going to do. So let's write down the given data. Okay, the given data. That's the data we got from the question. Okay, so for the first data we have here, we have the initial internal energy. Okay, so I name that as U1, okay, which is equal to 800 kilojoule. And then during the cooling process, the fluid lost 500 kilojoule of heat, right? Which is what heat going out of the system. So that'll be heat going out. Okay, and then that's negative. Okay, so you're going to have minus 500 kilojoule. Okay, so let's take note of this. And then the paddle does 100 kilojoule of work on the fluid, right? Which is what work input. Okay, and then that is what negative. So we are going to have W in to be minus 100 kilojoule. So let's take note of this. So we are fluid. Okay, so now let's go ahead. So with the system here, it is a closed system. Okay, that's when you look at this figure here. Okay, you see the rigid tank here, and then you have the fluid in it, and then we have the cooling process, which is what taking place by the paddle here. Okay, so what will happen is that since this system is a closed here, okay, the fluid in it is going to be stationary, right? Assuming you have a cap and then you have a T in this cap here, okay, we have a T in this cap here. This T is not going to be flowing, okay, it's not going to be flowing. And then if it is not disturbed, we can consider it to be stationary. So same situation here, okay, so you are considering this system here to be a stationary system. So let's look at that. We know that if a system is stationary, then the internal kinetic energy and then potential energy will be what? Zero. So we're going to have the non-flow energy equation. So we're going to have Q net minus W net, okay, to be equal to change in the internal energy, right? So in this case, since you've been given initial internal energy, okay, I'm going to rewrite the change in internal energy to be equal to U2 minus what? U1. Okay, so I'm going to have the equation to be Q net minus W net, okay, equals U2 minus what? U1. Okay, so now let's find Q net. In this case, we only have heat output here, okay, which is heat lost by the fluid, which is what? Minus 500 kilojoules. So I'm going to have minus 500 here, okay, and then minus the work input, which is also what? Negative. So that what? Minus what? 100 kilojoules. And then that will be equal to what? U2 minus what? U1, which is what? 800 kilojoule, right? So now let's do the simplification. So we are going to have minus 500 plus 100, right? Which will be equal to what? U sub 2 minus what? 800, right? So now when you do this, you are going to have minus 400, okay? Because U sub 2 minus what? 800, right? So now let's do the final calculation. I'll take the 800 to the left hand side, so we're going to have minus 400 plus 800, okay, plus 800, and then it should be equal to u sub 2. So adding this, we're going to have 400 kilojoule. Okay, that will be the value of what? The final internal energy. So we're going to have the final internal energy to be what? 400 kilojoule. Okay, so now let's try our hands on another example. Okay, so I have another example here which says that a gas trapped inside a piston cylinder device receives a 20 kilojoule of heat while it expands, performing a boundary work of 5 kilojoule. At the same time, 10 kilojoule of electric work is transferred into the system. Evaluate Q, W, and change U with appropriate sign. So you have to evaluate the net heat transfer, the net work, and then the change in internal energy. So the question says that a gas trap inside a piston cylinder device received 20 kilojoule of heat, right? Which is what? Heat input, right? Which is what? Input, which is what? Positive. So you're going to have Q in, right? And that's what? 20 kilojoule, okay? And then power of heat while it expands, performing a boundary work of what? 5 kilojoule. So this boundary work here will be work output, okay? That what? Work output. The boundary work will be the work done by the system, okay? So we're going to have work output to be equal to 5 kilojoule, okay? And then the sign for that is positive, okay? Work output is positive, and then we have heat input to also be what? Positive. And then at the same time, 10 kilojoule of electrical work is transferred into the system. So 10 kilojoule of electrical work is transferred into the system. So we have work input here also, which is what? 10 kilojoules. And we know work input is what? Negative, right? So that what? Minus 10 kilojoules. Okay, so this is what we have now. We have to evaluate Q, W, and then change in what? Internal energy. And then Q here is the heat transferred, and then W is what? The network. So now let's look at that. So you're going to find, sorry, the Q here is the heat transferred, and then the W is the work done by the system. So you're going to find the total heat transfer and then the total work, okay, total work done by the system, and then the change in internal energy. So now let's find the Q net. Okay, Q net, which is the same as the Q that we've been asked to find. So the Q net is the total heat transferred in the system. Okay, so you're going to have Q in, which is what? 20 kilojoule, right? That's the only heat transfer there, which is what? The heat in. So that's what? 20 kilojoule. So you're going to have the Q. Okay, you're going to have the Q to what? 20 kilojoule. And also you have to find the W, which are considered to be network done by the system. Okay, so that will be the sum of the work done by the system, which will be 5 kilojoule, right, plus minus 10. Okay, so when we do this, we're going to have 5 minus 10, right? That gives us what? Minus 5 kilojoule. So we have the net work done by the system to be what? Minus 5. So we're going to have W to be equal to what? Minus 5 kilojoule. Okay, you don't necessarily have to bring the W and then the Q again. Okay, the Q net here and then the W net already signifies those, but just for me to do what the question says, that's why I brought the Q and then the W again. So now you have to find the change in the internal energy. So generally, you know that the non-flow energy equation, we have Q net minus W net to be equal to the change in the internal energy, right? So now you know the value of Q net, which is 20 kilojoule, and then we know the value of W net, which is what? Minus 5, right? So that will be minus 5. Then that should be what? The change in internal energy, right? So we are going to have 20 plus 5. That should be what? Change in internal energy. So in this case, we're going to have the change in internal energy to be equal to what? 25 kilojoule. And then that's what? Positive, right? And then for the network, that was what? Negative. And then the net heat transfer was also what? Positive. So those are the appropriate signs that we have indicated here. So that's all for this video. Please make sure you like and subscribe for more examples.